Hello everyone, and welcome to this video on section 6.2 called Properties of Power Series. In this video, I'm going to be taking you through a preview version of a Newton Alta assignment for section 6.2 on Properties of Power Series. Please understand that the questions I see in this video may not be exactly the same questions that you see when you work on the assignment yourself. But the objectives are the same, and hopefully the problems are similar enough so that watching me do them here will help you when you work on the assignment on your own. All right. So here's our page, Newton Alta site, when we're working on our assignment. See the title of the assignment in the upper left corner. You will not see the word preview. In the upper right corner, you have your mastery bar, which shows you how far along you've gotten. Next to that, the activity log, which shows you how far along in each objective you've gotten. And it looks like there are 4 sub-objectives, 2 main objectives that you can switch between anytime you wish, and 4, sub-objectives in this assignment. On the main page, you have your current objective. Beneath that is a question related to that objective. And at the bottom of every question, you should have a feedback button. All right, if you see any typographical errors or any problems with the answer explanations or any other issue, you can send feedback directly to Newton, and hopefully someone will get back to you and fix the issue. You will not have this instructor cheat button. All right, this is for instructors only. But you will see a more instruction button if you're ever struggling with a particular topic or objective. Try clicking on this and it'll take you to a page with further reading to do or videos to watch or both, and you'll be given problems related to that instruction that you can work on while still having the instruction available on the same page. And you can work through the entire assignment this way. Every time you see a question with more instruction, you can click on that, go to some new problems, and work and finish the assignment like that every single problem. And there is absolutely no shame in that, nothing wrong with that at all. Okay, so the first objective I'm seeing here is called Create a New Power Series. Now, we did something similar to this in the section 6.1 video. So if you go back to the section 6.1 video, you'll see some problems where I'm doing this as well. And in all these problems here, we're going to take advantage of the fact that we know about geometric series and when geometric series converge. So let me refresh your memory here. So I'm going to have this written up in the last video, as I said. But let's recall, what we know about geometric series. And in fact, I'll put up the most basic version. So remember, if I have an infinite series, say the sum from n equals 0 to infinity of just, r to the nth power, where r was the, you have an exponential rule here, and r was called the common ratio for a geometric sequence and the corresponding series that I'm about to write. And when n equals 0, right, you got 1 plus and then r plus r squared and so on, right? And to get from one term to the next, you'd multiply by r. increase the power of r. So remember, if this common ratio, right, was between -1 and 1, or they might say, the absolute value of the common ratio is less than 1, same thing. Then our basic geometric series here will actually converge to something. The more and more terms that get added on, the closer and closer the sum gets to a specific value. The series converges, and it converges to the following. It would be the first term, which here is 1, divided by, and then 1 minus the common ratio. Right? Converges to, the first term 1 divided by 1 minus the common ratio. So more generally, this is general here. I would just replace r with something. But this is what I had up on the previous video in section 6.1. So whenever I'm going to make a little box here to replace r. Whenever the value of the expression in this box is between -1 and 1, this series, right, the sum from n equals 0 to infinity of, and again, all this box is doing is replacing our common ratio here. Box, something to the nth power is equal to 1 over 1 minus whatever's the expression in that box, right? So this is the concept we're going to be referring to quite often throughout this video. All right. Now, in this first example they're giving me, we have this sum. The sum from n equals 0 to infinity of 27 to the nth times and then x to the 3n power. Now, if I wrote out the first several terms of this, this would be 1, right, where everything's to the 0 power, plus, and then, 27 times x cubed, plus, then 27 squared times x to the 6th, and so on. We can see that this is geometric. And the common ratio is 27x cubed. Right? To get from one term to the next, I keep multiplying by 27x cubed, right? And we can also see that here if we rewrite this as just a single expression to the nth power. Pardon me. The sum from n equals 0 to infinity, and I can think of 27 to the nth and then x to the 3n as x cubed to the n, and then make this all to the nth power. It's 27x cubed to the nth power. Right, and what this will converge to, right, this will be equal to 1, right, the first term of the sum, divided by 1 minus the common ratio. Right, so 1 minus, again, the expression in the box here is the common ratio, 27x cubed, when 27x cubed is between -1 and 1. And then I solve this for x, and we get what's called, the interval of convergence, right? The values of x that I can plug into this series and have it be convergent. Right? When we talked about we saw interval of convergence and radius of convergence in section 6.1. But yeah, solve this inequality here for x to get the interval of convergence. Well, dividing through by 27, right, -1/27 must be less than whatever x cubed is, and that must be less than positive 1/27th. And since this is an odd power, right? Odd powers can be negative, right? We're okay here, and take the cube root of everything. So negative 1/3 less than x less than positive 1/3, right? Taking the cube root of everything. So here we go. This is what we're being asked for in the problem. This is called, the interval of convergence. Right? And we don't need to check the ends here because this is all geometric. When x equals 1/3 or when x equals negative 1/3, this 27x cubed would be equal to 1 or equal to negative 1, and a geometric series is divergent when the common ratio is 1 or negative 1. The common ratio needs to be between negative 1 and positive 1 for a geometric series to converge. Now they do want this in interval notation, right? So I'm going from negative 1/3 to positive 1/3, and I would put parentheses on both ends to indicate that, x can't be negative 1/3 or positive 1/3 for it to be convergent. Now they don't ask us what things converge to, but I wrote down here what it would converge to, right? If x was replaced with any of these values, any value between negative 1/3 and positive 1/3, this series, right, this infinite sum here would converge to this value, right? And then just replace x with the value here. But we just want the interval of convergence, right? So parenthesis in interval notation. All right, x can be anything from negative 1/3 to positive 1/3. Make sure there's parentheses and not brackets on those. All right, now after you submit an answer, you'll be given some sort of answer explanation, whether you're correct or incorrect. Now, if you are incorrect, definitely read through these. Hopefully you can figure out where you went wrong, why you were wrong, and you can fix that for future questions that are similar. If you're correct, I'd still recommend glancing through just to make sure you know that you're right for the right reasons, that you didn't just guess correctly. And who knows, maybe even in the answer explanations, they'll explain how to do something in a way that you like better and you can use for future questions that are similar. Okay. All right, so now we're asked to, again, create a new power series. All right. And this one has a nice product going on down here. So we're asked to construct a power series for the function, f of x equals 1 over x minus 15 times x minus 14. Now we could do this actually in a couple of ways. Notice it doesn't ask us for a specific center. Right? They don't say center the series at 1 or center the series at 0. And we talked about the center of a power series in the previous section, 6.1. They just want what can every term of our series look like here. All right, so construct a power series for the function. Now, in this section, all right, 6.2, if you look at the objectives, and you look at the construction, all right, create a new power series, or if you read through section 6.2 of the openstacks.org Calculus 2 text or Calculus Volume 2, Section 6.2 of that text, they talk about adding power series, combining. They talk about creating new series by multiplying series. So I'm going to go over this a couple different ways, and then I'll enter something in this box here, and hopefully it'll work out. If not, I'll see what they want with the instructor sheet, and maybe we'll use some enter some feedback to Newton, but we'll see what happens. So here's our series. So again, I'm going to keep this up. This is going to be used extensively throughout this video. Now the function we're given, f of x equals 1 over, and down here we have x minus 15 times x minus 14. Now you could multiply this out and try to write the denominator here as 1 minus something. That would be a little ugly in my opinion. My suggestion here, I think what they're trying to have us do, because of the fact that, this is nice and factored out already, factored to x minus 15 times x minus 14. I'm thinking they want us to write the partial fraction decomposition here. So hopefully you remember how to do that. If all my factors down here are linears, non-repeating linears. So this fraction here should be able to be expressed as a constant, say a over one of these over x minus 15 plus, and then another constant over the other factor, a b over x minus 14. And if I multiply through by the denominator, we'll get 1, then must be equal to a times x minus 14 plus b times x minus 15. And I could do equating coefficients on both sides, gather like terms and whatnot, but I'll do the thing where we just plug in some nice values. Like if x were 14, you could solve for b, right? B would have to be -1, right? You'd have 1 on the left equals negative b on the right. So b would have to be -1. And if x were 15, you'd have a equals 1, and then the term with b would be 0b. So this is when I rewrite a as 1, and then we have, minus 1 for b. So I can express this function 1 over, x minus 15 times x minus 14 as 1 over x minus 15 minus 1 over x minus 14. Then we can write a nice series for each of these and combine them. All right. So for the first one, 1 over x minus 15. Remember, if I pull out, I would like it to look like this instead. I got the 1 in the numerator, sure, but I'd like to have 1 minus something in the denominator, 1 minus some expression with the variable. And I'm going to keep it so that we're centered at 0, right? You saw in the last video in section 6.1, hopefully, that having the series centered at 0 was a lot nicer than having it centered somewhere else. So I'm going to pull out a -15 from the bottom here. This factor out -15. So I'll have -1/15 times, and then, 1 over 1 minus x over 15. Right, if you were to multiply the bottom by -15, you'd get your -15 and you'd get your positive x, right? And so now as a series, right, the thing in the box, right, I got this expression here, the 1 over 1 minus something, right, 1 over 1 minus something. The expression in the box is this x over 15. So we can say this is equivalent to the following series, whenever x over 15 is between -1 and +1. Or when x is between -15 and +15. Right? We can say that this is equal to -1/15 times the sum from, n equals 0 to infinity. I'm just replacing this box here with, it's over 15 of x over 15 to the nth power. Okay. All right, so when x is between -15 and 15, this first term of our partial fraction decomposition up here can be expressed as this series, and we'll do some rewriting in a little bit. And then the next series, the next, 1 over x minus 14, I could do something very similar. Pull out a -1/14 here, pull out a -14 from the bottom, and I'd have -1/14 times 1 over 1 minus x over 14, right? And then the term in the box, the expression in the box is this x over 14, right? So whenever x is between -14 and 14, basically, right, you would have x over 14 between -1 and 1, and then multiply by 14. So when x is between -14 and +14, this function can be expressed as the following infinite series, -1/14 times the sum from n equals 0 to infinity of, and then, x over 14 to the nth power, right? Yeah. Now, putting them together, right, this series up here converges when x is between -15 and 15. This series here converges when x is between -14 and 14. Now, they're not the same, right? Between -15 and +15, between -14 and +14. There are some values up here that this series won't converge to. So if I want them both to converge, we have to use the values that these intervals of convergence have in common. Right? So both series converge for the intersection, right? They call this the intersection. It's just what do the intervals have in common for the intersection of the intervals of convergence. Right, the intervals of convergence are -15 to 15 for the first series, and then this symbol here is the intersection symbol. It's like an upside down U. And then the second series converges for -14 to 14. Well, the only stuff they have in common is the values between -14 and 14. Right. So when x is between -14 and 14, right, belongs to this interval, our function, right, the one we were given, 1 over x minus 15 times x minus 14, the series we were given, when we put them together in this fashion, right, when we subtract them, will converge to our function. So remember, this is equal to 1 over x minus 15, which was this series, right, -1/15 times the sum from n equals 0 to infinity. Now this x over 15 to the nth, I'm going to write as x to the nth over 15 to the nth. So that's the first term of our partial fraction decomposition. Then we have minus the other series, right? The other series converges when we're between -14 and 14 as well. Now if I subtract this will be plus 1/14, right? Plus 1/14. So minus -1/14 plus 1/14 times the sum from n equals 0 to infinity. And again, this x over 14 to the nth, I'm going to rewrite as x to the nth over 14 to the nth. And we can start combining this stuff. Now, if I put the -1/15 in here, you'll have the sum from n equals 0 to infinity of negative, and then, x to the nth negative 1 over, and then 15 times 15 to the nth would be 15 to the n plus 1, plus, and then same thing with this 1/14. I'm going to put that constant multiple in this and distribute it into the series. The sum from n equals 0 to infinity of, just x to the nth over 14 to the n plus 1. And we can actually combine these, right? They have the same index, right? They both have index of n. They're starting at the same value, and they both have the same powers of x. Right? But because they have the same index starting at the same value, we can combine these to be the sum from n equals 0 to infinity of, and then the sum of these, negative x to the nth over 15 to the n plus 1, and then plus x to the nth over 14 to the n plus 1. And just because they have the same starting value, if this started at 1 and this started at 0, or this started at 0, this started at 3, or you couldn't do this. You got to have these series starting at the same value with the same index in order to combine them like this. And then one thing I'm noticing is that these both have x to the nth in common, so I can factor this out, and we have the following sum. Sum from n equals 0 to infinity of, now if I factor out x to the nth, all right, we'll have x to the nth, and then I'll put the positive term first, 1 over 14 to the n plus 1 minus 1 over 15 to the n plus 1. And here you go. This is what they're wanting. And the interval of convergence, right, IOC, negative 14 to 14. All right. So this series, as weird as it looks, when I plug in a value of x between negative 14 and positive 14, this series will converge to this value, right, the function we were given. And you can verify that, with some Desmos stuff, right? If I go to Desmos, I'm going to put in that function we were given, all right? Here was 1 over x minus 15 times x minus 14, all right? And I know it doesn't look great, but, there's some graph here. And I'll put up the values, the lines, x equals negative 14 and x equals positive 14, and I'll make those dashed. So there's green is positive 14, and the blue is negative 14. All right, we'll make them the same color. Same color, dashed lines. Okay, so what we're going to see is when we write the series up, all right, and I start putting more and more terms on the sum, adding more and more terms of our series, the function that our series represents will converge to the red graph here, but just in between these two blue lines, right? Outside it won't. Here was our sum. We had the sum from n equals 0. And I'm going to go from 0 to a, right, like I did in the last video, of, and then we got 1 over 14 to the n plus 1 power. Make sure that's all in the power. All right, then minus 1 over 15 to the n plus 1 power. All right, and all that times x to the nth, okay? And you're seeing, I'll start this at 0 and have it go up to, say, 50 by ones, right? Yeah, you see when it's 0, we get just this purple line here that matches pretty well the red graph in between there. Now, what you're going to see happening is the more and more terms that get added on, this curvy part near x equals positive 14 will also get matched. Let's play this and slow it down a bit. You'll see the more and more terms get added on. See this purple graph here, more and more terms get added on, starts slowly converging, right? But converging to this red graph, but just before the blue dotted line, right? Just between negative 14 and positive 14. And maybe I need more than 50 terms to be added on here, but you see the sum of the first, there's the sum of the first 50 terms there. It's getting close, right? It's slowly creeping up on the red graph. Let me go to let's do the first 100 and play it again. Oops, let's have it play the other way, please. All right, so there's the sum of the first. Let me slow it down again. There you see 65 terms, 66 terms, and so on. The more and more terms get added on, this purple graph is approaching this red one, but just before this x equals 14 line, right? And it's just matching. See to the left of negative 14, it doesn't match at all. It's just between the negative 14 and positive 14 lines. All right, so back here, in the box here, we have the sum from n equals 0 to infinity of, and then I'm going to enter the same stuff I had, 1 over 14 to the n plus 1 power, then minus 1 over 15 to the n plus 1 power, right, then times all that, come on, all that times x to the nth, and that should be enough. Yes. All right, they had it a little differently written out here with the brackets and whatnot, but it's the same value, so they said I nailed it. Great. All right, so yeah, see they did the partial fraction stuff and all the same junk I just showed you. Wonderful. All right, so now we're asked to combine power series. Here's determine the interval of convergence for the power series that can be used to represent the following function, centered at 0. All right, centered at 0. All right, so what I'm going to do is, again, you're going to see, like with the last example, I'm going to do a partial fraction decomposition here. All right. I know it doesn't look like ready for it yet, but remember, you can do that for any rational expression that's got a factorable denominator like this one does. So here's our function. We're given this 14x minus 1 over 2x squared plus x minus 1. Again, this is 14x minus 1 over, and then the denominator, factors to 2x and x, and we'd have plus 1 here, minus 1 here. 2x minus 1 times x plus 1. You can double check, right? 2x squared plus 2x minus x for the plus x, and then minus 1. So I've factored the denominator here to, linears, non-repeating linear factors. So then I should be able to express this fraction here as a sum of some simple fractions where there's a constant over 2x minus 1 plus, and then another constant, say b, over x plus 1. All right. And if I multiply through by the denominators, we'll have 14x minus 1 over here must be equal to a times x plus 1 plus b times 2x minus 1. And if x were equal to a half, right, the b term would go away. So we'd have 1.5 or 3 halves a equals, and then 7 minus 1, right, half of 14 times a half is 7 minus 1 is 6. Then multiply by 2/3, a must be 4. All right, so this is 4 up here, 4 over 2x minus 1. And then when x equals -1, the a term would disappear. And when x is -1, you'd have a -3b on the right side and -15 on the left side, right? -14 minus 1. Divide by -3, b equals +5. All right, so when I do the partial fraction decomposition, right, this function here is represented as 4 over 2x minus 1 plus 5 over x plus 1. Now, if I look at each of those fractions separately, 4 over 2x minus 1, and I try to rewrite them as, remember I want 1 over 1 minus box showing up. All right, we want this to show up somehow. And I can rewrite it as a power series. First off, I'll pull out a negative, and I'll also pull out -2, so that way we get, well, actually, I don't need to pull out -2. Let's pull out -1 here, and we'll get, negative coming outside on the bottom. I'll keep the 4 up top here, so this is -4 times 1 over, 1 minus 2x. And there's the expression in the box, 1 over 1 minus box. And it's something that would be, when I write it as a series, I'll have something centered at 0, right? It's not x minus 1. There's no quantity x minus something else here. It's just x, plain old 2 times x. So when this 2x is between -1 and 1, in other words, when x is between -1/2 and +1/2, we have a series that'll converge to this, right? This will be equal to -4 times the sum from n equals 0 to infinity of this, 2x to the nth power, right? Or 2 to the nth times x to the nth, whatever. But the interval of convergence for this is, values from -1/2 to 1/2. So that's for the first part of our partial fraction decomposition, the first term. The second fraction, 5 over x plus 1, we can think of that as 5 times, 1 over. Now, x plus 1 is the same thing as 1 minus -x. That's x plus 1. So the expression in the box this time is -x. So here, when, -x is between -1 and +1, again, that would just mean that x would be between -1 and +1. We get a series that would converge to this. We can write a series that'd be 5 times the sum from n equals 0 to infinity of -x to the nth power, some alternating series, -1 to the nth times x to the nth. But the interval of convergence here is -1 to 1. I need the intersection of both of these. If I want both, we need both of these to be convergent. We need sums that converge to both these things. So this converges to the first term between -1/2 and 1/2. This converges to the second term, right? This series converges to the second term, second fraction between -1 and 1. Well, the only values they share are between -1/2 and 1/2 then, right? Put them together, do their intersection. The interval of convergence for our series, the sum of these series would be values, between -1/2 and 1/2. That's the only values that both will converge for. And that's all they ask for here. They just want, you got these series centered at 0. What would be the interval of convergence for the series, when you put them together? So -1/2 to +1/2. And that's all. Great. And again, read through the answer explanations, please. Now, they actually put it all together, but all they wanted was this interval of convergence. Great. All right. Here, pretty much the same thing. We're going to be doing a partial fraction decomposition for this fraction, this rational function. And we're going to create a couple power series centered at 0 and put them together, right, by adding 2 power series. Right. So we have the fraction given to us is 19. The function is 19x plus 9 over x squared minus 1. And you can think of this as 19x plus 9 And then this denominator, right, is the difference of squares. That'll factor to x minus 1 times x plus 1. And we have some non-repeating linear factors once again. So when I do my partial fraction decomposition, I could break this up to a proper fraction, some constant a over x minus 1 plus, and then some constant b over x plus 1. Multiplying through by the denominators, we get 19x plus 9 must be equal to a times x plus 1 plus b times x minus 1. When x equals 1, I can solve for a. We'd have, 19 plus 9, we'd have 28 over here equals 2a. So a would be 14, right? So this is a 14 over x minus 1. And if I want to solve for b, I could easily let just x equal negative 1. On the left side here, that'd be negative 19 plus 9 is negative 10. And over here, it'd be negative 2b. So b must be positive 5. Right? So we have 14 divided by x minus 1 plus 5 over x plus 1. This sum would be equal to our function. And I could create a nice power series that'll converge to each of these. And we got to do the, take the intersection of the intervals of convergence for these so that they both converge to our original function when we add them together. So the first term there, 14 over, x minus 1. If I pull out a negative from the bottom, that'll be negative 14 times the quantity, 1 over 1 minus x. And the thing in the box down here is just 1 minus x, right? So as long as x is between negative 1 and 1, we have a series that'll converge to this, right? It'll be negative 14 times the sum from n equals 0 to infinity of just x to the nth power. All right, and then the other one, 5 over x plus 1. Now we saw x plus 1 or 1 plus x in the last example. I can think of this as 5 times and then 1 over 1 minus negative x. Right, so this time the thing in the box is negative x. So once again, as long as x is between negative 1 and 1, right? Because negative x being between negative 1 and 1 is the same as x being between negative 1 and 1. We get a series, the following series, that would converge to this. So 5 times the sum from n equals 0 to infinity of negative x to the nth. And we're adding these together, and it's got the same both of them have the same interval of convergence, so their intersection is just this, right? So the interval of convergence is between negative 1 and 1. And then for values of x between negative 1 and 1, this series plus this series will equal our function, or will converge to our function. So we're taking the sum from n equals 0 to infinity, and then you have, negative 14 times x to the nth plus, and then here it'd be 5 times negative 1 to the nth, and then, factoring out x to the nth from all those. So all the coefficients would look like this. It'd be 5 times negative 1 to the nth minus 14. All the coefficients look like that, and then times your powers of x. This is what they want us to fill in here. The coefficient expression, and then your x to the nth. So the coefficient expression, I have negative 14 plus 5 times, and then negative 1 to the nth. Right, those are your coefficients times, and then just straight up x to, they want it centered at 0, so I want just powers of x minus 0, or just x to the nth. Great. Okay. Again, please read through the answer explanations. All right, so once again, creating a new power series. We're asked to determine the interval of convergence for the function represented by the series below. Write your answer in interval notation. and join multiple intervals with a union symbol if necessary. Okay. All right, so pulling this up, right, this series we're given. Sum from n equals 0 to infinity of 1 over x minus 4 to the 3n plus 1 power. And we're asked to determine the interval of convergence for such a series. Now we could try the ratio test here. All right, if I think of this as a sub n, remember how we were determining the interval of convergence in the last section, right? Section 6.1. We can always do that again here. I mean, it's the same question, right? Determine the interval of convergence. So I'm going to find this limit, and I'll try to look at it some other way as well after this, just to see if there's a clearer way to do it. But this is never a bad start when asked to determine the interval of convergence for some power series. So we have the limit as n approaches infinity, remember, of the absolute value of the n plus first term to the nth term. What happens is, what happens to the ratio of every term to the term before it, as you go down the series. Limit as n approaches infinity of the absolute value. Now the n plus first term is this, where you replace n with the quantity n plus 1. So that'd be 3 times n plus 1, which is 3n plus 3, and then plus 1 again. So 3n plus 4. This would be 1 over x minus 4 to the 3n plus 4 power, right? Again, that's 3 times the quantity n plus 1, and then plus 1 again. And then dividing by an, dividing by the previous term is just this, dividing by this. But dividing by this is the same thing as multiplying by the reciprocal. So multiplying by x minus 4, to the 3n plus 1 power over 1. Now, a lot of stuff's going to cancel here, right? This would be the limit as n approaches infinity, the absolute value of. This down here, this is x minus 4 to the 3n plus 1 times x minus 4 cubed. That would be 3n plus 4. So we're getting this canceling with this, and then you're just left with 1 over x minus 4 cubed. And you notice now how there's no more n in this. This is considered constant. And remember, the limit of the constant was just itself. So this is the absolute value of 1 over x minus 4 cubed. Now the question becomes, when is this less than 1? Right, remember, when this limit of this ratio, right? Remember that when this limit was less than 1, the series will converge. And then we have to check the ends. Remember, when the limit equals 1, this test is inconclusive, and we gotta test it out. All right, so when is this less than 1? Well, that means, 1 over x minus 4 cubed must be between -1 and 1, right? Because it's absolute value. Absolute value being less than 1 means you're between -1 and 1. And the only way the only way, if this were positive and less than 1 and I flip things, it'll be greater than 1. And if this were negative and greater than -1 and I flip it, it'll be less than -1. So when I do the flips here, this splits. This would mean that x minus 4 cubed would have to be less than -1, or x minus 4 cubed would have to be greater than 1, positive 1, right? Because if you're greater than positive 1 and you do the reciprocal, you'll be less than positive 1. And if you're less than negative 1 and you flip it, you'll be greater than negative 1. Okay. And still negative, right? You're same thing. If you're greater than 1 and flip, you'll be less than 1 and positive. So definitely greater than negative 1. So like these have had to, one of these has to happen in order for this to happen. Now here, cube root both sides, x minus 4 must then be less than negative 1. Right. And then you add 4, x must be less than 3, or same thing here, cube root x minus 4 must be greater than 1. Add 4, x must be greater than 5. So we'll see that x could be less than 3 or greater than 5. Right? So my interval of convergence right now are numbers, I can plug in numbers less than 3 and the series will be convergent. I can plug in numbers greater than 5 and the series will be convergent. We must also check where is this equal to 1, and that'll be at x equals 3 and x equals 5. Right? When x equals 3, this absolute value will be equal to 1. When x equals 5, this absolute value will be equal to 1. So I got to also check 3 and 5. Sorry that those are tiny there. So check when limit equals 1. All right, just like in the last section, or the section on the ratio test as well. So when x equals 3, all right, go back to our sum here. When x equals 3, this would be negative 1 to the 3n plus 1 power. Now negative 1 to the 3n, I'll just write this up. The sum from n equals 0 to infinity of 1 divided by, and then negative 1 to the 3n plus 1. Now negative 1 to the 3n plus 1, this is negative 1 to the first, right? So there's negative 1 times, and then negative 1 cubed to the nth. So this is the opposite of negative 1 to the nth. And of course, if I divide 1 by this, multiply by the reciprocal of this is basically just the opposite of this sum, which is definitely divergent. We've seen this before. This would just be 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. Not going anywhere. The partial sums will always be 1 or 0. You're not actually approaching any specific value. So that's not involved in our interval of convergence. And then when x equals 5, we get the sum, 5 minus 4 is 1, 1 to any power is 1. This would just be the sum from n equals 0 to infinity of 1, which should be definitely divergent, right? 1 plus 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 the sequence, the terms of the sequence that you're adding up are always 1. So definitely divergent, all right? So the interval of convergence here are all the values less than 3 or the values greater than 5, right? That's what they're saying. Use the union symbol if there's a break in here. Here's your interval of convergence. So interval notation, right? Negative infinity to 3. Union, and they got the union symbol here, and then from 5 to infinity, but parentheses on the 5, right? We said 5 was not making that series convergent. Okay, so they rewrote it this way instead. And yeah, pretty much we're like, hey, when is this ended up showing me the same thing, when is this 1 over x minus 4 cubed, when is that going to be between negative 1 and 1, which is what we solved. All right, so maybe I'll do the next problem like this, the way they did it here, to show you the two different methods. I mean, again, the ratio test never hurts. It's always a good way to determine an interval of convergence for a power series ratio test, or even the root test sometimes. All right. Okay, we did something similar to this. All right, but this time they only want the interval of convergence for a series that would converge to this, and I'm hoping they mean centered at 0. They didn't really tell me centered at 0, but I'm assuming it's centered at 0. So yeah, we did something similar to this one before. But now instead of writing the series, right, again, they just want the interval of convergence. So our function is this 1 over x minus 10 times x minus 9, which I should be able to write as some constant over x minus 10 plus some constant over x minus 9, which if I don't worry about finding the constants right now, down here I could pull out, a over negative 10, and then we'd have times 1 over, and then 1 minus, x over 10. Plus, and then here, same thing, you'd have, b over negative 9, so negative b over 9 times 1 over, and then 1 minus x over 9. And so when I write series here, if I'm trying to find power series that converge to these functions, here we need x over 10 to be between negative 1 and 1, so x to be between negative 10 and 10. Here we would need x over 9 to be between negative 1 and 1, so x to be between negative 9 and 9, and then I'm doing the intersection of these, right? In order for both to converge, right, both our series to converge to this function, both parts of this sum, we need the intersection, which will just be these values from negative 9 to 9, right? These are the only ones they share. So the interval of convergence here is just the values between negative 9 and positive 9, right? So parentheses, negative 9, comma, positive 9, close parentheses. All right, now they actually probably write out the entire thing. They find the series. They don't find the series, but they find the constants, right? Again, you don't really need to find those constants when you're doing the partial fractions to determine the intervals of convergence. All right, construct a power series for this function. They don't say anything about having it being centered at 0, so I'm assuming it's going to be centered at 0. Right? That's usually the easier center for a power series. Right, but using the same concept we've been using throughout with that geometric series. So we have 6x squared divided by 1 plus x to the 9th, which I can think of as 6x squared times 1 over 1 minus negative x to the 9th. All right, so then this, when this negative x to the 9th is between negative 1 and 1, now of course that's only going to happen when x is between negative 1 and 1. All right, so there's the interval of convergence. I'll just put IOC. Right? So when x is between negative 1 and 1, we'll have a series that converges to this. Right? We'll have 6x squared, and then our sum from n equals 0 to infinity of negative x to the 9th to the nth power. The common ratio, replacing that expression in the box. Now I can rewrite this as negative 1 to the nth times x to the 9n, and then putting the 6x squared in, we get the following sum. So from n equals 0 to infinity of 6 times negative 1 to the nth, there's the coefficients. And then x squared times x to the 9n, that'd be x to the 9n plus 2. And you would add those powers. So they want that. And this series will converge to our function value only when we replace x with values between negative 1 and 1. But 6 times negative 1 to the nth for the coefficients, and then your powers of x to the 9n plus 2. So 6 times negative 1 to the nth times x to the 9n plus 2 power. Great. Yeah, all these problems, as you've been hopefully noticing, depend on your knowledge of that geometric series concept, and they keep repeating it in the answer explanations. Okay. So back to combining power series. Right. Now, here's the product, right? Determine the interval of convergence for the product of the power series. It works the same as for a sum. If you were to multiply two power series, you know, and you want the product to be convergent, well, then the two factors, the two series you're multiplying, must be convergent, right? So you need the intersection again, right? We need to have the values that both converge for in order for their product to be convergent. So this, again, works for products, sums, all right? So we have -8, f of x equals -8 over 1 minus 5x cubed. All right, this is, just -8 times 1 over, 1 minus 5x cubed. This 5x cubed, right, if that's between -1 and 1, we can write a convergent series, a series that converges to this. And that's going to happen then when x is between the cube root of -1/5 and the cube root of +1/5, right? So the interval of convergence for our series here, we'd have -8 sum from n equals 0 to infinity of this, 5x cubed to the nth, which would be 5 to the n times x to the 3n. That'll converge to f, right? This series will converge to f on this interval, where x is between the cube root of -1/5 and the cube root of +1/5. G, right, this other function g they gave us is -2 over 1 minus 6 x to the 8th. Again, I can think of this as -2 times, 1 over 1 minus something. And the expression in the box here, right, 6x to the 8th. When 6x to the 8th is between, -1 and 1, now, because x to the 8th, that's an even power of x, this will never be below 0. And then we have 0 less than or equal to x to the 8th less than 1/6. And now when I take the 8th root, we'll get absolute value again. Right? Absolute value of x to the x of x must be less than, the 8th root of 1/6. And this implies that x must be between, the opposite of the 8th root of 1/6 and the positive 8th root of 1/6. All right. So there's the interval of convergence for this series. Right, we'd have -2 times the sum from n equals 0 to infinity of 6x to the 8th to the nth, right? So 6 to the nth and x to the 8th. The product, right? Again, just like a sum earlier, f times g has a power series with interval of convergence. That's the intersection of these two. Yeah, intersection, that upside down U, right? What do these have in common? Where do both of our series converge, right? In order for the product of these two to converge, I need them both to be convergent, right? If one of these diverges, then their product will not converge, or the product will diverge. So I need them both to be convergent. So again, we're doing the intersection here. Now, which numbers are bigger, which numbers are smaller? I could do some sort of logarithm thing, but I'm just going to go to a calculator. See which one of these is bigger, which one's smaller. Clear all this stuff from a previous problem out. Blow this up a bit. All right, so we have, 1/5 and the cube root of 1/5, so raised to the 1/3 power, that's about 0.58. And then the other interval of convergence involved 1/6, the 8th root of 1/6, all right, so 1/6 to the 1/8 power, which is bigger, all right. So this interval up here is from about negative 0.58 to positive 0.58. And the interval for this other series is from about negative 0.79 to positive 0.79. So again, what they have in common is just between these two, right? So this interval here is what they have in common, right? Outside these, you're getting in here, but the second will converge, but the first one won't. If you're above 0.58 but less than 0.79, the second will converge, but the first one won't. Yeah, the only ones that they share, the only values they share are these negative, cube root of 1/5, positive cube root of 1/5. All right, and that's what I'll type here. So we got the cube root. They don't have a nice little root thing. Yeah. All right. So I'm just going to do like I did in the calculator for Desmos, raised to fraction powers. So negative 1/5, right, to the 1/3 power, right? Cube root of negative 1/5 on the low end, and positive 1/5, to the 1/3 power, the cube root of 1/5 on the high end. All right. Okay. They wrote it with it's a little simplified here with cube roots, but yeah. And again, it's just like sums, right? It's these sums and products. In order for the sum or product of series to converge, both series need to converge. So you're looking for the intersection, of the individual intervals of convergence. Where do they overlap? All right. Okay. So this is actually multiplying some series. All right, so they're saying find the first four non-zero terms of the product of the power series for these two functions. And that would construct, the first four non-zero terms of a power series for their product, right? Notice that this f here is just the product of these two, right? So negative 2 over 1 minus x to the 7th multiplied by negative 3 over 1 minus x to the 4th would be, positive 6 over 1 minus x to the 7th times 1 minus x to the 4th. And they're already giving us the interval of convergence for these series, negative 1 to 1. We're just asked to find the first four non-zero terms of their product. So this involves a lot of distributing, right? Multiplying polynomials, but you're also, multiplying these polynomials with infinitely many terms. So that's kind of why they're not having you write out a really extensive, sum with the summation notation here. They're just having you write out the first four terms. So, negative 2 over 1 minus x to the 7th. When x to the 7th is between negative 1 and 1, which would imply that x is between negative 1 and 1, this would be equal to the following series. The sum from n equals 0 to infinity of, negative 2 times x to the 7th to the nth. So x to the 7n. All right. Putting the negative 2 in, and then you have x to the 7th to the nth power, so x to the 7n. Now, if I write out the first several terms of this, this would be a negative 2, and then I keep multiplying by x to the 7th, minus 2, x to the 7th, minus 2, x to the 14th, minus 2, x to the 21st, and so on, right? The other series is negative 3 over 1 minus x to the 4th So again, same deal, this x to the fourth, in order to have a series that converges to it, x to the fourth must be between -1 and 1, and that'll happen when x is between -1 and 1 as well. So when x is between -1 and 1, here's a series that'll converge to this function, sum from n equals 0 to infinity of, -3 I'll put inside here, and then you'd have x to the fourth to the nth, so x to the 4n. And if I'll write out the first several terms of this, you got, this would be -3 for the first term, then -3x, and then keep multiplying by x to the fourth, -3x to the fourth, -3x to the eighth, -3x to the 12th, and so on. We are multiplying these series. So we'd have, this times this. That'd be +6 over 1 minus x to the 7th times 1 minus x to the 4th. Well, again, it would just be like multiplying this polynomial by this polynomial. All right, this polynomial by this polynomial. Now remember how to multiply polynomials. Take every term from one, distribute to the other. So first I start off by distributing the 2. So I'll just take the first term here. So I'm going to stack some terms here. Now -2 times -3 is +6. -2 times -3x to the 4th be +6 x to the 4th. And then +6 x to the 8th. +6 x to the 12th. +6, blah, blah, blah. All right. That's when I distribute the -2. And then I get more and more. Now, next I move over and I distribute the -2 to x to the 7th. So I'll get +6x to the 7th, and I'll put that here, +6x to the 7th, and then +6x to the 11th. Right? I should have left some more space here. These aren't going x to the 11th, and then +6 x to the, x to the 15th, and then +6 x to the 19th, and so on. Right? And then I'll distribute the -2x to the 14th to these. So it'll be +6x to the 14th, which again really won't go with any of these up here. And then the 18th, +6x to the 18th, and so on. And I'm noticing that after that, you get 21st and then 25th. And when I do the 21, my lowest 4 terms here, nothing's really getting combined are these. All right. These 4 terms here are the lowest powered terms. So when I'm writing this out, this will be 6 plus 6x to the 4th plus 6x to the 7th plus 6x to the 8th plus 6x to the 11th plus 6x to the 12th plus 6x to the 14th, the 15th, the 16th, then the 18th, 19th, 20th, 21st would be next. Like be a lot more terms to put out there, but they're only asking for what would be the first 4 non-zero terms, and there you go. So it's a lot involved here, but after a while, maybe they'll see, oh, and I'm not going to get any terms that are like these that would add with these, so those will be the first 4 on their own. So the first term of the sum would be 6, and then 6x to the 4th. And then 6x to the 7th would be the next highest powered term. And then finally 6x to the 8th would be the next highest powered term. And that's it. And of course, there's many, many, many more. There's infinitely many more. That would be the first 4 non-zero. You can watch how they're doing it here, read through the answer explanations. Okay, they did pretty much exactly like I did. All right. Here's the same thing, given a couple power series here. So if I set the functions that have power series that converge to them for values of x between -1 and 1, again, so I don't have to find the interval of convergence that's given to me. And if I were to multiply those power series to create a power series for this new function over this interval, what would be the first 4 non-zero terms? So very similar problem as the last example. Okay, so we have 6 over 1 minus x to the 7th. Again, that would just be the sum. As long as x is between, absolute value of x is less than 1 here, all these sums will be convergent to our functions. Sum from n equals 0 to infinity of 6 times x to the 7n. And so this is 6 plus 6x to the 7th plus 6x to the 14th plus 6x to the 21st, and so on. Then our other function, 4 over 1 minus x to the 4th, right? When x is between -1 and 1, this series will converge to this function, 4x to the 4n. So it's 4 and then plus, 4x to the 4th plus 4x to the 8th plus 4x to the 12th and so on. And now I'm multiplying them. So multiply these, you get 24 over this 1 minus x to the 7th times 1 minus x to the 4th down here. And again, the power series for this, for values of x between -1 and 1, first I'll distribute the 6. You got, 24 plus 24x to the 4th plus 24x to the 8th plus 24x to the 12th and so on. Then I distribute the next term, the 6x to the 7th, the plus 24x to the 7th plus 24x to the 11th, plus and so on. And then I'd get 14th and then 14th, 18th, 22nd. The first 4 non-zero terms are going to be these, right? You're not going to have any powers lower than 8 after that. So here are the first 4 non-zero terms of this power series. Right? So very similar to the last problem. So 24, 24x to the 4th, 24x to the 7th is the next highest power, and 24x to the 8th. And that's it. Great. Very, very similar problem. Okay, and then here, determine interval of convergence for the power series. So we did one, again, similar to this before. So I'm going to do partial fraction decomposition here. And without actually finding the series, we'll just look at the denominators. We can say what the interval of convergence of each term of the sum is, and then do their intersection, right, to find the interval of convergence for the whole series, or the combination. So the function we're given this time, 47x minus 7, divided by, and then 5x squared plus 4x minus 1, right? That denominator factors to 5x minus 1 times x plus 1. Right, that'd be 5x squared, and then plus 5x minus 1x for the plus 4x, and then minus 1. Who cares what's up here? It's just something with a lower degree. So when I break this up, it'll be some constant over 5x minus 1 plus some constant over x plus 1. And then when I look at the series for these, if I try to express them as power series, this down here I can put as a over -1, so negative a times 1 over 1 minus 5x plus, and then here I would just pull out and just make this b, don't pull out anything, over 1 and the 1 over 1 minus negative x. So here negative x needs to be between -1 and 1 for us to have a convergence, a series that converges to it, represented as a power series, meaning x has to be between -1 and 1. Here 5x would have to be between -1 and 1, meaning that x would have to be between -1/5 and positive 1/5. And then we do the intersection, which will just give us these values here. The only values these share are the ones between -1/5 and 1/5, right? So if we have series that converge to these, in order for both to be convergent at the same time, the value of x we'd plug in would have to be between -1/5 and positive 1/5. So there we go, -1/5 to positive 1/5. Great. All right, so that's half of the objectives done. Wonderful. Next topic. All right, so now we're differentiating. So the stuff left is differentiating and integrating power series. So we can do them just like polynomials, right? Differentiate and integrate term by term. And what you're going to see is, and I'll write this up, if you have a power series with a certain interval of convergence, the derivative series and the integral series will have the same interval of convergence, except maybe at the ends. All right, so you know what? I'll just write that up right now. So remember what a power series looks like. So say you have the sum from n equals 0 to infinity of c sub n times x to the nth, and we'll just do a power series centered at 0. So say that's f of x, right? Some function of x. All right, so this would be c0 plus c1x plus c2 times x squared plus c3 times x to the third, and so on. And let's suppose the interval of convergence is from negative r to r, right? Remember where r was the radius of convergence, and it's centered at 0, this one. If it's centered at x equals a, you'd have a different value, but in the middle. Now, when you do the derivative, f prime, remember that would just be nothing, right? 0 plus, and then c1 plus, and then 2c2x plus 3c3x squared, and so on. So we have the sum to infinity of, and every single term here that actually is non-zero looks like this, c sub n, and then you're just doing we're doing your derivative up here, right? It was c sub n, and then x to the nth, right? You use the power rule, you'd have n times c sub n times x to the n minus 1. But notice I'm not starting at n equals 0 here. Right, we don't have 0, c sub 0, blah, blah. The first non-zero term is at 1, so this is going to start at 1. Sum from n equals 1 to infinity of n times c sub n x to blah, blah, blah. Same interval of convergence. All right, same interval of convergence, but you may have to check the ends. All right, so I'll put this up. Check the ends. All right, it's just like differentiability, back in Calc 1. Y equals square root of x. That was differentiable and that function's defined at x equals 0. But when I do the derivative, that'd be 1 over 2 root x. That's not defined at 0. So that's just an example of something similar when it comes to where a function is defined. When you do the derivative of a power series, you'll get the same interval of convergence, but I'll box this up again, put exclamation points on it. You must check the ends as well. You may also include the ends. They might make this new series work. Same thing for the integral. Right, when I integrate f of x with respect to x here, so you'd have do the right side, it'd be c0x plus, and then c1 over 2 x squared plus, and then c2 over 3x cubed plus c3 over 4 x to the fourth. And you also remember when you do indefinite integrals, you throw on this constant of integration, right? So we got this c plus, and then the sum from, and notice the first non-zero thing is starting at n equals 0 again. And it's just c sub n over n plus 1 times x to the n plus 1, right? You're just taking the terms from the original series and integrating, reversing the power rule term by term. Now, this constant of integration, we may have to find, and the same thing with the interval of convergence. It has the same interval of convergence as the original function, but you may have to check the ends, right? You might have increased the size of it and added those values on the ends. But you have the negative r to r, or a minus r to a plus r if it's centered at a, and you're going to have to check the ends when you integrate. So back to our problem. All right, so we're differentiate power series again, and it says evaluate the sum of the series. Enter an exact answer. All right. So again, like in pretty much every problem we've seen in this video, we're going to start off using what we know about a geometric series. So back here, so before we get to this problem, actually, talk about our geometric series again, but this time I'll write it as a power series. All right, so we got the sum. Oops, sorry, that's drying out on me. All right, so the sum from n equals 0 to infinity of just, basic x to the nth power, right? We had r to the nth earlier, or, a picture of a box to the nth earlier. But this would be 1 plus x plus x squared, and so on. And as long as x was between -1 and 1, right, or the absolute value of x is less than 1, this would converge to a function, right? 1 over 1 minus x. I'll call this, f of x. So it's 1 over 1 minus x. Now here we're going to be differentiating, right? I'm in the objective differentiate power series. So if I were to differentiate this, right, f prime of x, well, that would be, again, 0. Then remember how this started at n equals 1, the derivative from the previous page? So the sum from n equals 1 to infinity of, and then every single thing would be n times x to the n minus 1 power. Right, that would be 1 plus 2x plus 3x squared, and so on. Now I could also, if I wanted to have this start at 0, just replace n minus 1 with n. So bear with me here, watch this, right? So if I wanted to have n start at 0 instead, or my index start at 0, I could have x to the nth, replace n minus 1 with n, but then n would be, n minus 1 plus 1. So when I replace it with n minus 1 with a new n, that'd be n plus 1. That's the original is like having n minus 1 plus 1. And I'm replacing these n minus 1s with a new n that starts at 0. And you can see that this would give me the same series, right? When n equals 0, I'd have 1 times x to the 0, so 1. When n equals 1, I'd have 2x to the first. Then when n equals 2, I'd have 3x squared, right? So you can change indices, change, the starting values, as long as you're changing all the corresponding parts of the expression. And again, as long as x is between -1 and 1, right? So you have the same interval of convergence, but we might have to check the ends. This function will converge, or this power series, sorry, will converge to the derivative of this. Now this is 1 minus x, to the -1. When I differentiate this, this would be negative, 1 minus x to the -2, then times -1 again because of the chain rule. So this would be 1 over 1 minus x squared is what this sum would converge to, right? The derivative of 1 over 1 minus x with respect to x. And then if you were to check the ends, you'll see that we get divergent stuff. If you check the ends here, if I were to replace x with -1, you'd have an alternating series. You'd have 1 minus 2 plus 3 minus 4, but the terms of that wouldn't be going to 0. and non-decreasing, so it'd be a divergent alternating series. And of course, if x were 1, you'd have 1 plus 2 plus 3 plus 4 plus 5, definitely divergent. So we have divergence at both ends. So we still have the same interval of convergence for this series, a series like this. Okay, well, the series in question is this. We're given this series, the sum from n equals 0 to infinity of n plus 1 in the numerator divided by 5 to the 3n minus 1 in the denominator. And we're asked to say what this converges to. They're telling us this is convergent. What does this converge to? Now, I see this sum from n equals 0 to infinity of n plus 1 times something. Again, based on our knowledge of the derivative of a geometric series, I'm getting something like this. So I would like something to the nth power next to that. So I'm going to manipulate this a bit. We got the sum n equals 0 to infinity. All right, so I've got the n plus 1. Now 5 to the 3n minus 1, that's the reciprocal of 5 to the 1 minus 3n. Right? So that's like having times 5 to the 1 minus 3n. And 5 to the 1 minus 3n, that's the same thing as 5 times, and then 5 to the negative third power to the nth. I can pull 5 out. So this would be 5 times the sum n equals 0 to infinity, and then you have your n plus 1, and then 5 to the negative third, that's 1 over 125, right? 1 over 5 to the third to the nth power. And you see how this sum here is just this sum, where x is 1/125th. Right? You see I got the sum from n equals 0 to infinity of n plus 1 times something to the nth, right? N plus 1 times something to the nth. And as long as that thing being raised to the nth power, the x is between -1 and 1, which 1 over 125 is definitely between -1 and 1, this will converge to 1 over 1 minus that x squared. All right, so this should converge then to 5 times, and then our series here converges to 1 over the quantity 1 minus 1/125th, squared, which this will be 5 times, now this is 124 125ths squared, and then you're doing 1 over that, so that'd be a reciprocal. This would be 125 squared over 124 squared, or 125 or 124 squared. And honestly, I can just enter it like this. This is the value this series will converge to. So back here, this sum will converge to 5 times, and then the quantity, 125 over 124 squared. Right. And if we want to double check that, verify it a little bit, maybe with some calculator work, here's the sum we were given. I was given the sum from n equals 0 to, and I'll just go up to x. All right, I'll put in different values for x. Look at the table of n plus 1 divided by 5 raised to the 3n minus 1 power. And make a table for this, put in different values of x. See, when some of the first 11 terms from 0 to 10 will be 5.08 something. So it's 5.08 something, right? In fact, after I put in 10, the decimals aren't changing after a bit. So this series will converge to 5.080970, and this decimal place might be 3 or something that rounds to 3. Now, I did say what this should, now hopefully when I punch in what I typed in the on the assignment, what we said it would converge to actually starts off this way. It's 5.0809703. So we had 5 times, and then 125 124ths this squared, right? And you see this 5.080973, right? That's what this series is converging to. So this should be good. Yeah, it's checking it out. Yeah, it's exactly the way they typed it. Now, if I wanted to multiply it all out in one single fraction, you could, but you know, didn't feel like it. And it looks like that's the way they're typing it too. All right, moving on. All right, so another differentiate a power series. Okay, so this is asking, find the interval of convergence for the power series representing f prime if f is, this. Okay, so remember the interval of convergence for the derivative of a function or the integral will be the same in between the ends, but you have to check the ends as well. Differentiating or integrating may include the endpoints all of a sudden. So I'll write this function up. We'll put out a series for that series representation for it. So the function we're given here is -4 divided by -3 plus x to the 6th. I'm going to express this as a power series and write the interval of convergence for that series. Now, if I want, 1 over 1 minus something involved here, I'm going to have to factor out 4/3, right? A -4, a negative. So I pull out 4/3. This will be equal to times 1 over and 1 minus, x to the 6th over 3. Because again, if I multiply this by -1 over -1 to be +4 over 3 minus x to the 6th. Well, this is +4 over 3 minus x to the 6th, right? Okay, so then here's the expression in the box, 1 over 1 minus box here. So as long as, this x to the 6th over 3, when this is between -1 and 1, we have a series that'll converge to this function. And if you solve this would be x must be between, the negative, or do absolute value in junk, but this would be negative, 6th root of 3, and the positive 6th root of 3, because again, the even power always be, so we have x to the 6th would be from 0 to 3, and then 6th root, and we get absolute value of x must be between, what must be less than the 6th root of 3, right? So x must be between negative 6th root of 3 and positive 6th root of 3. So there's the interval of convergence for this series I'm about to write. So when this is happening, when x is between these two values, our original function, this power series converges to our original function, 4/3 times the sum from n equals 0 to infinity of, and then you have your x to the 6th over 3, and for the box, right, to the nth power, where the common ratio would go. All right, well, so f of x on this interval is the sum from n equals 0 to infinity of 4 times x to the 6th n power. And then down in the denominator here, you'd have 3 to the nth times 3, so over 3 to the n plus 1. All right, so when I differentiate, if I look at the first several terms of this, right, when n equals 0, you have 4/3 plus, and then 4/9 when n equals 1 times x to the 6th, then blah, 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 right? So when I differentiate, here's what the series will look like. It's a sum from, again, when you differentiate, starts at 1 now, right? N equals 1 to infinity. Keep the coefficient thing, but then I'm multiplying by, doing the power rule for x to the 6th n. So this would be 4 over 3 to the n plus 1. X to the 6th n, when I do the power rule, would be 6n times x to the 6th n minus 1. So I'd have 24n, all right? over 3 to the n plus 1 power, which I can probably simplify in a little bit, times x to the 6n minus 1. Now the interval of convergence, x should be between negative 6th root of 3 and positive 6th root of 3. Now we check the ends. All right. Now here's the thing with this. X to the 6n minus 1, that's x to the 6n, then divided by x, and yeah, maybe I can mess with this a little bit. I'll just keep it this way for now. Now, if I check the ends, when I plug in negative 6th root of 3, here's what we're getting. We got the sum n equals 1 to infinity of 24. Now 24, I can do this. That's 8 times 3, right? And then cancel one of these 3s. So this is 8 over 3 to the nth instead. So it's 8 over 3 to the n times n, so 8n over 3 to the n, and then times, and then I'm replacing x with, negative 6th root of 3, or 3 to the 1/6 power here, to the 6n minus 1. Well, when I raise this to the 6n, negative 6th root of 3 to the 6n power, and then divided by, negative 6th root of 3 to the to the first. This, right, negative 6th root of 3 to the 6th power would just be 3. So this is 3 to the nth up here, and then divided by, whatever negative 6th root of 3 is down here. And then 3 to the nth in the denominator there, 3 to the nth in the numerator here. So this ends up being the sum from n equals 1 to infinity of, 8n, 8 over negative 6th root of 3 times n, which is definitely divergent. The terms would be going to infinity. Right? So definitely a divergent series. So that's not included. And then when x equals positive, all that would change is that this would become positive down here. So that'd be this. So it's divergent either way. So there's our interval of convergence from, the x can be anything from negative 6th root of 3 to positive 6th root of 3 for the derivative, right? If I wanted a power series for the derivative. So interval notation, parentheses, from the negative 6th root of 3, so I'm going to go 3 to the 1/6 power, to positive 6th root of 3, 3 to the 1/6 power. Get that down there. That should be good. Again, they explain how at the same interval of convergence, where you have to check the ends, see, substituting x equals negative 6th root of 3, positive 6th root of 3, right? Okay. Great. All right, this one's integrate power series. So once again, I'm going to write up what we know about our geometric series, right? We know when that converges. And then when you integrate, right, it'll have the same interval of convergence, just maybe not at the ends, right? So just like with differentiation, you'll have to plug in the ends to see if you have a convergent series or not. Additionally, with integration, you're also going to have to determine that constant of integration, right? A capital C. So I'll write that up again here. Right? So with geometric series, though. All right, so let's go back to what we know about our geometric series. So again, this sum, right? The sum from n equals 0 to infinity of just x to the nth. So remember that's 1 plus x, same start as the last one, last objective. And if x is between -1 and 1, this series will converge to 1 over 1 minus x. And again, I'll call this capital F, not capital F, but little f of x. All right, so interval of convergence for your geometric series -1 to 1. Now when I integrate and get a new function, integrate with respect to x, well, that would be all this, integrated with respect to x plus, half x squared plus a third x cubed and so on. But then you also have plus some constant of integration here. So yeah, so this series is our normal series. It's the sum from n equals 0, starting at 0 here to infinity of, and then just take your power series for the geometric and integrate. You reverse the power rule here, so it'd be x to the n plus 1 over n plus 1. Right, and you can see when n equals 0, you get an x. When n equals 1, you get half x squared. So it needs to start at 0, this one. But you got plus this constant of integration that needs to be found, right? We're going to find this, and the value of this depends on what function we're converging to. And again, as long as we're in this interval, all right, as long as x is between -1 and 1, we'll get this series here converging to the integral of this. Now, the integral of 1 over 1 minus x would be the natural log of 1 minus x, the absolute value of 1 minus x, times -1, or divided by -1. This is negative, natural log of the absolute value of 1 minus x. Right. And then to find c, if I put in, say, 0 for x, we'd get 0 on this side, and then all these would be 0. And so c must be 0 as well. But we'll do that when we look at the individual functions that we're talking about. Okay. So the example I'm looking at, they give us this function. So ours might not involve a natural log here. Oh, I'll just write the integral, because like this function we're about to look at isn't very nicely integrable. So here, function, 1 over 1 minus x is no problem. All right, integrating that's no problem. The function I'm looking at here that they're giving me in this first problem, 7 over 6 plus x to the 6th. Yeah, integrating this would be a lot tougher. Right? It wouldn't involve, I mean, it might involve a natural log, but I don't think so. Might also involve an inverse tangent. But again, I'm not actually going to try integrating this. What we're going to do is rewrite this as some series, with some specific interval of convergence. So if I pull out 7/6 here, we have 1 in the numerator and then 1 plus x to the 6th over 6, which would be minus negative x to the 6th over 6. All right, I'm trying to get 1 over 1 minus something like I have been in all these. So basically, when this expression here, right, the negative x to the 6th over 6 is between negative 1 and 1, we can represent this fraction here as a power series. I don't know if I get this, is it be between the 6th root of 6 and negative 6th root of 6, basically, right? Multiply by 6, do 6 roots. So basically, here's our interval of convergence, right? When x is between negative 6th root of 6 and positive 6th root of 6, we can represent this function f as the following series, 7/6 times the sum from n equals 0 to infinity of, this thing in the box here, right? This negative x to the 6th over 6 to the nth power. I'm going to mess with this, right? This will be, so f of x, as long as we're in this interval, right? As long as values of x are in this interval, f of x will be the value of this series here. We have the sum n equals 0 to infinity of 7 times negative 1 to the nth, right? This would be negative 1 to the nth times x to the 6th n over, and then 6 to the n plus 1 power. Right. So there's your coefficients and your powers of x. And it's centered at 0, right? These are powers of just x, not x minus 1 or x minus 2 or something. So if that's the power series, right, the integral of f. Now this will not, again, I don't know how to, I don't know that the integral of this fraction, this rational function off the top of my head. And I think it would be a little tough to do, actually. But even though we don't know how to integrate this just yet, we can still express it in terms of a power series that converges, for certain values of x. So the integral of f with respect to x, and is going to be some constant, right, which we'll determine in a second, plus, and then, well, we don't really have to determine this. All they're asking for is the interval of convergence in this problem. So that's probably why they're giving me a function that's difficult to integrate. They don't really expect you to integrate that. They're just asking for the interval of convergence for this new series. So I integrate term by term. We'll have some constant of integration plus, the sum from 0 to infinity of, constants here, 7 times negative 1 to the nth over 6 to the n plus 1. And then we integrate all this, there'll be times x to the 6n plus 1 power divided by 6n plus 1. All right. So there's our new series. This is going to be the same interval of convergence, right? So again, IOC x, in order for this to converge to whatever this integral is going to be, x needs to be between, negative 6th root of 6 and positive 6th root of 6. But just like the last example, I need to check the ends, right? Doing this integration of power series or differentiation of power series could just tweak the ends a bit. Still the same in between. You still have the same interval normal otherwise, but we have to check the ends. All right. So I'll do that on the next page with this series here. All right, with this series. So when x equals, negative 6th root of 6, this series I'm looking at is this. You got the sum n equals 0 to infinity of, 7 times negative 1 to the nth over 6 to the n plus 1 power. And you got, 6n plus 1 in the denominator here. And then negative, 6th root of 6 to the 6n plus 1 power. Now 6 to the n plus 1, that's 6 to the nth times 6. And this negative 6th root of 6 to the 6n would just be 6 to the n times, and then negative 6th root of 6, to the first. So times negative 6th root of 6. And so 6 to the n's would cancel. You'd have 6 to the n in the denominator, 6 to the n in the numerator. And so we're getting actually a convergent alternating series. You see, this is a constant, the 7 is a constant, the 6 is a constant. I could pull that out. You'd have 7/6 times, negative 6 root of 6. That comes out. Sum from n equals 0 to infinity of, and then just negative 1 to the nth over 6n plus 1. This is an alternating series, right? You got negative 1 to the nth there, so it's plus minus plus minus plus minus. And then the terms that you're alternating, right? 1 over 6n plus 1, those are decreasing to 0. So this is a convergent alternating series, right? You do the alternating series test. So the interval of convergence for this integral, right, the series that represents this integral of f, includes that left end, whereas the series representing the original function would not include it. Right? And the same would go for the other one. When x equals positive root 6, all that would change with this becomes positive, positive, and positive out here. Everything else should remain the same. All this crap would cancel. I'd be left with this convergent alternating series. So both ends actually work. When I plug in negative 6th root of 6 or positive 6th root of 6 for x, this series will converge to some value, plus some constant that'll be equal to whatever the integral of that function is at that value, all right, with the value of that value of x plugged in. So I'm moving brackets on this, right? The interval of convergence includes the n's this time. So bracket, negative, and then the 6th root of 6 I'll write as 6 to the 1/6 power, comma, and then positive, 6th root of 6, 6 to the 1/6 power, and then close the brackets. Both ends are actually making that series for the integral convergent. All right. Again, read through the answer explanations. I'll just slowly scroll. You can pause, do whatever. Okay, great. All right, so another integrating a power series. All right, so we're asked to find a power series representation for the following function by integrating the derivative, right? If you want a function f, we can find the derivative of f and then integrate to go back. If we're talking about doing series for things. All right, so you'll see. So this is the function we're given. F is equal to, negative 2 times the inverse tangent or arctangent of 8x. Now look at f prime. This is not a rational function. This is not something that we could express with some geometric series like we've been doing for almost, all these problems. But look at the derivative. Where the derivative would be negative 2, and the derivative of inverse tangent of something was 1 over, 1 plus that thing squared. But then times the derivative of that thing, right, chain rule. So this is negative 16 times 1 over, and then 1 plus 64x squared, which would be 1 minus, negative 64x squared. And here we go. See how the derivative has 1 over 1 minus something involved. So when this negative 64x squared is between negative 1 and 1, which would imply that x must be between 1/8 and negative 1/8. I'm going to divide by 64, take square roots and all that. So there's the interval of convergence for our series I'm about to write. When x is between negative 1/8 and positive 1/8, we have a series that'll converge to f prime. That'll converge to this function, right? F prime would be equal to, negative 16 times the sum from n equals 0 to infinity of, and then this negative 64x squared, right, the thing in the box, to the nth power. All right, which I will rewrite in another way here. This is negative, 2 to the fourth out here, negative 1 times 2 to the fourth, sum from n equals 0 to infinity, and then, negative, you'd have a negative 1 to the nth to cause some sort of alternating, right? And then 64 is 2 to the 6th power, so it'd be 2 to the 6th to the n, so 2 to the 6n power, and then x to the second to the n would be x to the 2n power, right? And then I put this in at the sum from n equals 0 to infinity. Now negative 1 times negative 1 to the n, that would be negative 1 to the n plus 1, still an alternating series. Then 2 to the fourth times 2 to the 6n, you'd have 2 to the 6n plus 4 power, and then still x to the 2nth, right? So here's the coefficients, and then times your powers of x, right? And it's centered at 0. These are powers of just x. All right, so this series, when x is between negative 1/8 and positive 1/8, this series will converge to this function, right? The derivative. So then if I want this, right, a series that would converge to this, we need to integrate, right? Go back. So we have a series for the derivative. Let's integrate that. The integral of f prime, with respect to x, that would just be f. Right, so we're getting a series that'll represent negative 2 times the tangent of 8x, or inverse tangent, sorry, of 8x. And so remember, when we integrate a series, we're going to have some sort of constant of integration that I need to find, plus, and then sum from n equals 0 to infinity, and then I keep the constants the way they are, right? You got negative 1 to the n plus 1 times 2 to the 6n plus 4, and then we're integrating these powers of x, right? We'd have x to the 2n plus 1 power divided by 2n plus 1, and that would go with the coefficients. Now, to easily find the constant here, right, if I want to find that c, we can plug in a nice value of x. Well, a nice value of x here would be x equals 0, right? If x equals 0, this function, right, negative 2 times the inverse tangent is 0. The inverse tangent is 0 is 0, so I have 0 on the left equals c plus, and then when x equals 0, every single one of these terms over here would be 0. Right? When n equals 0, you'd have x to the first, then you have x cubed, then x to the fifth. Everything over here would become 0, so we get c equals 0. So that's nice. That gets rid of this constant. So here's a series for our function, right? So this sum, right, again, c is 0. The sum from n equals 0 to infinity, negative 1 to the n plus 1 times 2 to the 6n plus 4 divided by 2n plus 1 times x to the 2n plus 1 power. This series will converge to this value, negative 2 times the inverse tangent of 8x, when x is between, negative 1/8 and positive 1/8. All right. But we got to check the ends though. Remember this was the interval of convergence for f prime. I integrated. So I'll get the same in between, but we must also check the ends. All right, now negative 1/8, that's the same thing as negative 2 to the negative 3. Positive 1/8 is 2 to the negative 3. All right, so I'm going to plug those in. Because the powers of 2 here, that should make these nice. So I'll plug in the left end. So when x equals negative, 2 to the negative 3, negative 1/8, here's what the sum looks like. Sum from n equals 0 to infinity at negative 1 to the n plus 1 times 2 to the 6n plus 4. divided by 2n plus 1 times, and then we would have, you know, negative 1 to the 2n plus 1 times 2 to the, and then when you have 2 to the negative 3 to the, this is being raised to the 2n plus 1 power. So I up to the 2n plus 1 power here, right? To the 2n plus 1 power. That's why I got negative 1 to the 2n plus 1, and then 2 to the negative 6n minus 3. Right. Well, multiplying a bunch of this junk, negative 1 to the 2n plus 1, that's always negative 1. Because that's an odd number. 2n plus 1 is odd. And negative 1 to an odd is negative 1. And then put with this other negative 1, we get, negative 1 to the n plus 2, which would still cause alternating. And then 2 to the negative 6n minus 3, 2 to the 6n plus 4. That's just 2 to the first. So I pull times 2 over 2n plus 1, and we're taking this sum. This is a convergent alternating series, right? You got power negative 1 that's changing every term, and then 2 over 2n plus 1 will be decreasing to 0. So this is a convergent by alternating series test. So this series will converge to this value when x equals negative 1/8. And then if I change this to positive, that just changes this to positive 1. And that's pretty much it. So I'd have this, but with, negative 1 to the n plus 1. So it'd be exactly the same pretty much, another convergent alternating series. So both ends are included for this, this integral series. So this series will converge to this value for values of x between and including negative 1/8 and positive 1/8. Oh, ha, didn't need to do any of that, right? It shows you to read the instructions. All they wanted was a series for this function. All right, so all they want was this expression here. I got my constants times powers of x, right? This sum of these terms will be equal to negative 2 times the inverse tangent of 8x. Now, if they asked for the interval of convergence, that would only be true if x were from negative 1/8 to positive 1/8, right? But I'm going to type in this. All right, so we had our constants were powers of negative 1, right? Negative 1 to the n plus 1 power times 2 to the 6n plus 4 power divided by 2n plus 1. And all these were multiplied by powers of x, and it was x to the 2n plus 1 power. There's your series that would converge to negative 2 times the inverse tangent of 8x, as long as x was, from negative 1/8 to positive 1/8. All right, they wrote it totally differently, but I have something equivalent to that, so they told me it was good work, right? Wonderful. All right. Yeah, they don't even mention the interval of convergence here. They should. Right? Remember, they should talk about interval of convergence, right? If you're doing series work, infinite series, you should mention interval of convergence for power series, right? When does this converge? Because it's not, if it's going to diverge, there's no point in talking about it. Okay, so this one they just want the series again. They're not asking for the interval of convergence, so this time I won't. I'll still bring up the interval. Because again, you should. When you're talking power series, you should bring up an interval of convergence. Where does it converge? Where does it diverge? All right, so here's F. We'll write a series for this and differentiate. Notice how it's starting at n equals 1, right? Because remember, when you differentiate, the derivative starts at 1. Now you can do some little changes to make it start at 0, but the general derivative there started at 1 for these power series. Okay. So here was my function. F of x equals 5 over 6 minus x cubed. Then I can rewrite this, I'll pull out 5/6 here. times 1 over, and then 1 minus x cubed over 6. That'd be 5 over, and then 6 minus x cubed. So here's a series, right? Or here's a 1 over 1 minus box, right? That can be expressed as a series. So when this x cubed over 6 is between -1 and 1, we can express our function as a power series. Now this solving for x here would imply that x has to be between the negative cube root of 6 and positive cube root of 6, right? Multiplying by 6 doing cube roots. So there's the interval of convergence, right? When x is between these values, here's a series that will converge to f. Be 5/6 times the sum from n equals 0 to infinity of, and then just your 1 over 1 minus box is, sum of box to the nth, right? X cubed over 6 to the nth, which if I rewrite some stuff here, this will be the sum from n equals 0 to infinity of 5 times x to the 3n power over 6 to the n plus 1, right? You have 6 to the nth and then another 6 down there. So your coefficients are all 5 over some power of 6, and then all the powers on x are multiples of 3. And when I differentiate, the first term of this should just be a constant, 5/6 when n equals 0. So I differentiate that when n equals 0 term is gone. So I'm starting the next series, the derivative series at n equals 1. And it would just be 5 over 6 to the n plus 1. And then you're differentiating this power of x, right? Times 3n times, x to the 3n minus 1 power. And if you want, 3n times 5 is 15n. So there we go. I'll put this in. Or maybe I'll put in 15n in the numerator. This series, for these values, would converge to whatever the derivative of this function is. But we're not asked about any of that. So sum from n equals 1 to infinity of 15n over 6 to the n plus 1 power. Right, there's your coefficients. Times, and then the powers of x are x to the 3n minus 1 power. Right. Great. And then they don't really mention, again, they don't mention the interval of convergence, right? But it would have the same interval of convergence, right? This series would converge to whatever the derivative of this function is for these values, but you then would have to check the ends as well, right? Does this series converge for the values, negative cube root of 6 and positive cube root of 6? But we're not asked about that, unfortunately. Okay, this one we are asked about, the interval of convergence. All right, so find the interval of convergence for the power series representing this function. All right. So this is very similar to the one we saw before. We actually saw a problem very similar to this. I believe it had -4 in the numerator and I believe -3 plus x to the 6 earlier, but we'll still write it out. So here's f. Again, the -5 over -8 plus x to the 6, which if you multiply the top and bottom by -1, 5 over 8 minus x to the 6, and then I'll pull out 5/8. This will be 5/8 times, 1 over 1 minus x to the 6th over 8. So I got 1 over 1 minus something when x to the 6th over 8 is between -1 and 1, which would imply that, x has to be between -6th root of 8 and +6th root of 8. When x is between these values, we'll have a series that converges to our function here. That'll be 5/8 times the sum from n equals 0 to infinity of this x to the 6th over 8, to the nth power, which will be the sum from n equals 0 to infinity of 5 over 8 to the n plus 1 times x to the 6th n, right? Your coefficients times powers of x. Okay, so there's a series that'll converge to f, converge to this function, but for these values, right? Now, the series for f prime would be just, again, this, starting at 1, though. Again, the term when n equals 0 is constant here, so when I differentiate it, it'll be gone. So the derivative series will start at 1, sum from n equals 1 to infinity. Now, when I differentiate x to the 6n, that'd be 6n times x to the 6n minus 1. So I'd have 30n, 5 times 6n in the numerator, divided by 8 to the n plus 1 down here, and then times, x to the 6n minus 1 power. It should have this same interval of convergence, right? So when x is between here and here, this series will converge to whatever the derivative of this function is at that value of x, but we must check the ends, right? Check the ends. And you're going to see when I plug these in for x, the 8 to the nth will go away, and you'll be left with some constant here. You can pull it out. You'd have just the sum of n, and that's obviously divergent. The terms wouldn't be going to 0. So it's divergent at either end. I'll just leave that to you. But if you were to check the ends, this series will be divergent. All right, again, this is very similar to a problem we saw earlier. So the interval of convergence for this derivative series, power series, is just from negative 6th root of 8 to positive 6th root of 8, but not including the ends. The series for the derivative will diverge at the ends. So parentheses, negative. Now the 6th root of 8, I'm going to write as 8 to the 1/6 power, comma, and then positive 6th root of 8, 8 to the 1/6 power, and then close the parentheses, right? These ends are not included. All right, great. All right. And then this one is like one we saw again, where here's a function f. We can write a series for it, and then differentiate. And what would the derivative look like? So this is pretty similar to something we've already seen. I'll do it again though. All right, nothing, no harm in it. So here f is negative 3 over negative 2 plus x to the 9th, which I can rewrite as 3 halves times 1 over 1 minus x to the 9th over 2. Hopefully you see that. Now this is 1 minus something down here. So I could express that as a sum, when x to the 9th over 2 is between negative 1 and 1, we can express we can write a series that'll converge to this function. Now, if x to the 9th over 2 is between negative 1 and 1, that would imply that x is between negative 9th root of 2 and positive 9th root of 2. So there's our interval of convergence, but again, they're not asking about that. They just want the series. This would be equal to 3 halves times the sum from n equals 0 to infinity of our thing in the box to the nth power, x to the 9th over 2 to the nth. And if I put the 3 halves in, that would be the sum from n equals 0 to infinity of 3 times, x to the 9th is our powers of x over, and then 2 to the n plus 1 power, right? 2 to the nth times 2. That's the series for f. Now when I differentiate, again, when n equals 0, this will be some constant here. So when I differentiate, that term's gone. So the sum from n equals 1 to infinity for the derivative of, and then when I differentiate this x to the 9n, 9n will come down, there'll be 27n over 2 to the n plus 1 times x to the 9n minus 1 power. And this is what they want us to enter, right? And this series could converge to whatever the derivative of this function is for values of x between, negative ninth root of 2 and positive ninth root of 2. Now you would also have to check the ends, and I would see that, just like the last problem, they diverge. So there's our interval of convergence, but they only want what the series is looking like. All right, sum from n equals 1 to infinity of, the constants are 27n divided by 2 to the n plus 1 power, and then times the powers of x. You have x to the 9n minus 1 power. Wonderful. All right, and then we're going to finish off the last objective here. The last objective is on the integrals, right? All right, so this is another one where they just want the form of the series. So notice they already have here the constant of integration. They just want what the rest of it would look like. All right, what are we adding after that? All right, so the function we're given is, again, something I can express as a geometric series, or some multiple of a geometric series. So f is, 8 over 7 plus x to the fourth, which I can think of as 8/7 times 1 over 1 minus negative x to the fourth over 7. All right, because that'd be 1 plus x to the fourth over 7, minus negative x to the fourth over 7. So as long as this thing in the box here, all right, the negative x to the fourth over 7 is between negative 1 and 1, so meaning that x has to be between negative fourth root of 7 and positive fourth root of 7, right? When x is between those values, we can write a series that'll converge to this. This will be 8/7 times, and then the sum from n equals 0 to infinity of this negative x to the fourth over 7, right? This thing in the box here, to the nth power. That's like the common ratio of a geometric series. And if I multiply some stuff out here, right, this will be the sum from n equals 0 to infinity. You got 8 times negative 1 to the nth over 7 to the n plus 1. And then your powers of x are x to the 4nth. And then I'd be integrating. All right, they want the series. What would be the series that would converge to the integral of this function? Now, I don't know what the integral of this is. It's not a nice one. It's not like going to be natural log or something. But if I were to integrate that function, what series would converge to that function, it's going to be some constant of integration that we could probably find, plus, and then I'm doing the integral for every single term here. Now, when you integrate, the 0 term doesn't go away, right? It's when you differentiate, the 0 term goes away, so I start at 1. But integrating, I'll have some constant of integration plus, then the sum from 0 to infinity still, and then I got my coefficients, 8 times negative 1 to the nth over, and then 7 to the n plus 1. And then when I integrate this power of x, all the powers of x here, you got x to the 4n plus 1 power, and then divided by 4n plus 1, so I'll put the quantity 4n plus 1 in the denominator here. And here you go, right? This is what they want us to enter. And this should be the interval of convergence. We'd have to check the ends, of course. All right, check the ends, but this should be the interval of convergence. If x is between negative fourth root of 7 and positive fourth root of 7, this series, plus whatever this constant is, would converge to whatever the integral of this function is. Right. This is what I'm entering here, right. The stuff after the summation notation. So our constants, we have our constant multiples, 8 times negative 1 to the nth divided by 7 to the n plus 1 power times the quantity 4n plus 1. And then times, your powers of x here are, x to the 4n plus 1 power. That's what the series would look like for the integral of that function. Great. All right. This one, they're asking for an interval of convergence. Okay. I think we did something similar to it, but I'll write it out again. So our original function is this rational, right? Something we can express as a geometric series, right? 9 or some multiple of a geometric series, right? 9 over 8 plus x squared, which I can think of as 9/8 times 1 over 1 minus something, and that thing would be negative x squared over 8. This would give, these are equal. All right, so the thing in the box here, the 1 over 1 minus box, is negative x squared over 8. So as long as that's between negative 1 and 1, we're good. Well, that would imply that, when negative x squared over 8 is between negative 1 and 1, I mean, x is between negative square root of 8, so 2 root 2, or square root of 8, and positive square root of 8, positive 2 root 2, negative square root of 8, positive square root of 8, whatever. As long as x is between those two values, we have a series that will converge to this function, right? This will be equal to 9/8 times the sum from n equals 0 to infinity of, and then the thing in the box here, negative x squared over 8 to the nth. Which, if I write this a little bit differently, multiply some stuff out, put the 9/8 inside, you got the sum from n equals 0 to infinity of 9 times, you got negative 1 to the nth here, and then your denominator of the coefficients would be 8 to the n plus 1, and then the powers on x would be x to the 2nth. All right, so then integrating, we'd get some constant of integration plus the sum from n equals 0 to infinity of 9 times negative 1 to the nth over 8 to the n plus 1 times the quantity 2n plus 1 times, and then your powers of x would be x to the 2n plus 1. All right. This series will converge for these values of x, but we must also check the ends. All right, I'm just going to say these ones, because when I put in square root of 8 or negative square root of 8, you're going to see this x, square root of 8 to the 2n plus 1, you'll have 8 to the nth canceling here, and then there'll be some constant. Pull that out, and then you'll have a power of negative 1 over 2n plus 1. I promise you. If you plugged in either one of these, you'll get some power of negative 1 that'll cause it to be alternating. All right. Over 2n plus 1. And 1 over 2n plus 1 decreases to 0, and it's alternating. So for either one of these, we're going to get a convergent alternating series, right? So this is the interval of convergence for our integral series. This series will converge for any of these values here, and it'll converge, plus whatever this constant of integration is, it'll converge to whatever the integral of this is, which would involve some inverse tangent. All right, hopefully you can see that, but not asked to do that, right? Just what would be the interval of convergence? So this time I'm doing brackets. Negative square root of 8 to square root of 2 to positive square root of 8, positive 2 root 2. And then close brackets, because again, at either end, I plugged in either one of those and I saw some convergent alternating series appearing in my head. Great. So just be aware again that when you have a series, you differentiate it, you integrate it. The interval of convergence will be the same, except for maybe the ends, right? You got to check those ends when you look at the derivative series or the integral series. Great, and that should be it. Yeah, that looks like about it for this assignment. Great. And as I said at the top of the video, the questions I saw here, right, may not be the exact same questions you see when you work on the assignment on your own, but they are similar enough, hopefully, that watching me do them here helps you out, when you work on them yourself. And thank you very much for watching.